Hello everyone, welcome to the course Applied Artificial Intelligence. Today our topic will be system-wide learning. So today we'll dive into the possibilities that we have to learn across different entities to capture generalizable knowledge, not only for a single entity, for example, a division of a company or for a network of different companies, but overall knowledge. And how do we do this with a tool set that modern machine learning methods give us? But first, let's have a look at the objectives of this lecture. The first thing I want you to understand is the challenges that we face when we think about system-wide learning, because there are many, and there are also many ways on how we can address them. More precisely, the concepts that we can utilize are the ones of meta machine learning, transfer machine learning, and federated machine learning, as well as the different sub-concepts that are associated with those. So that's the second objective. Third, I want you to get to know a few examples from the real world, from our research, where we applied these methods, specifically meta machine learning. And then finally, I want you to be able to know when to apply which concepts if you learn about the different pros and cons of these. Okay, so let's dive in. The agenda for today is, first I want to do a very quick recap of AI in systems, and then talk about the challenges in system-wide learning, and then present to you three solutions: meta machine learning, transfer machine learning, and federated machine learning. So at the beginning of this course, we very shortly talked about systems. And I want to give you a short recap on that. So the idea of working in systems, or to be more precise, in service systems, is the fundamental understanding that value is co-created because multiple entities collaborate with each other. And that doesn't only mean the traditional view of having one service provider and one service client, but a complex network that co-produces value. If you recall, we had a bunch of examples for that, like a car wash or a smartphone, how this network of different app providers, for example, and then also of clients, make a platform worthwhile, right? So value is co-created, can only be produced because multiple entities work with each other. And if we believe in that, then of course the question is, how can we now utilize machine learning in such systems? Which brings us to system-wide learning. If you've worked in practice before or experienced real-world cases, you know that in many cases, data sources are distributed. They might be distributed within the company, but in many cases, they are distributed across company borders. Let's take credit scoring as an example over here. So if you want to know how likely a single customer is to pay back his or her loans, those customers typically have multiple bank accounts, and they also might have multiple credits running at the same time. But you as a single bank can only view the data of your own customers. So if a new customer applies, what do we know about this customer? Typically not a lot. So that's why learning across systems is immensely important, right? If we could do this across banks, then we could know or be better at doing the credit scoring for a new incoming customer. I know, interestingly, there is a system like that in Germany called the Schufa, which is not necessarily related to AI predictions, but in general, it is that same idea. However, in other countries, you do not necessarily have that kind of service, right? So data about customers is typically distributed, and if we want to learn something about them, we would need to have access to a lot of different databases located at different companies, right? First example. Second example, which you can see on the right there, is in industrial production. Let's say in an automotive production plant. Let's say we want to predict failures of your final product. Now, your final product consists of many sub-products that come from a lot of different vendors, but we cannot see into the production plans of these vendors. We can only see the products coming out. Now, for predicting downtimes or failures in productions, it would be immensely helpful to understand what's going on in these vendors. But as they lie outside our company borders, we cannot have access to that data. So as you can see, that is a very typical case in the real world. Now we ask, what challenges can appear when you analyze data coming from different entities? In order to do that, we have to make one fundamental assumption. Now, we know that these systems, these service systems, are increasingly digitized and they produce a growing amount of data. What we have to assume, though, is that this data is digitized in the first place, right? So that we have systems in place that capture data of the processes, right? Of the production plant, that we have processes capturing financial data, right? So we assume that the data is there, but we also assume that it's isolated, right? You can see 4 different entities over here which produce value in a system, and they all have their data, right? Data on the same customers potentially, data on the same product that will be later assembled into a car, right? Of a shared interest, if we could peek into these data sources of these entities. Now, what we know if we look into literature is that utilizing this data represents a major challenge for these entities. That's what the literature says. Now, with all the tools that are available to us and that we experienced so far in this lecture, we can of course address these analytical capabilities by utilizing machine learning, right? Very traditional, like you remember. We capture known data, train a model. This supervised machine learning model will then receive unknown data at inference time and will make prediction outcomes, right? Very basic things that we covered so far. The question now is, however, how can I make use of all the data that is available right there? The view that we have right now is for a single entity doing predictions, but what we want to do is we want to do holistic predictions across entities. So first thing that could come to your mind is, why don't we take all those data sources and put them into one large model, right? So we have a new entity that captures all the data that was previously isolated. Now, the main issue with that is obviously data exposure. These are different legal entities, and potentially a lot of their IP is in there. So that's a big risk, obviously. But I think this is a good starting point to dive into system-wide analytics. So I have these 2 extreme cases. The isolated analysis on the left, meaning every entity does its own analysis and nothing is shared. And the other extreme case is the centralized analysis on the right here, where we put all the data into one part and then do analyses. And for these 2, I want to highlight 3 different challenges that arise. The first one being data privacy. So a manufacturing company, let's take the car example that we had earlier, does not want to make process parameters available. May be public or may even be to their peers, which might also be potential competitors, because of course they expose their entire intellectual property, or in short IP, when they do that, right? That is their magic. That's what they've been working on for many, many years, to optimize these production parameters and make sure that whatever they're producing it in the best way possible. But due to a lot of their internal knowledge, their internal secrets, you might call them, and of course, they do not want to expose this. And by the way, there are, of course, laws protecting that data as well, especially once it comes to data that is related to real persons, right? GDPR, right? The protection of personal data is very, very important. So it's not only IP, but it's also personal data, right? And as you know, specific laws apply to these cases in the European Union. So data privacy, data IP is the first large challenge that we can see. The second one is data heterogeneity. So if we stick to the example of the production plant, we need to simultaneously analyze a lot of different types of data. So images coming in from the cameras who want to make sure that the quality of the parts is satisfying. We have text data coming from the people working on the machines, writing documentation. We have sensor data coming in, and those are all very fundamentally different data types, and somehow we need to work with that, right? This can lead to a lot of inefficiencies and complications in the analysis of that data, as you know already, right? So that's the second big issue. And the third one is data velocity, data volume, two of the V's from the big data definition, right? As modern sensors have higher and higher resolutions and the bandwidth of data gets higher that they transmit, there might be cases where this transmission is tough, especially if you try to transmit data for a production plant in the US to one in Munich or in Stuttgart. And that's one thing, but also that data has to be processed. Let's even say we can transmit it. It has to be processed in real time. Our model needs to infer predictions based on this data coming in. So these are three typical issues that we have to deal with when it comes to system-wide learning. Now, let's have a look back at the two cases that we mentioned earlier. And let's first look at the isolated analysis again, one of these extremes. And let's say every entity analyzes its data separately. So to make this example really, really clear, we have three different entities, A, B, and C, and they all have their own data. And this data might vary, right? Think of the challenge that we had one slide earlier with the data heterogeneity. So that means one of the vendors, entity A over here, might have numerical data. This vendor over here might have categorical data. And this one also has numerical data, but only integers, right? It's an example to make clear that data is heterogeneous across these different entities. But what we also want to think about is that they all work on a shared or common goal, right? So all of the three parts that these entities produce, they will later be assembled into an overall product, like a car, for example, or a different industrial machine, right? So it would be beneficial to know more about the current production status or current quality of one of these products for the other vendors, because later it's going to all be combined, right? So that's what this AAB symbolizes over here, is that we are talking about instances that will later belong together, right? So there is, of course, a shared key, a shared interest. But in the case of isolated analysis, however, all of these entities do their analysis alone, right? So they have the data sets, they build a machine learning model, and they're outputting frequent recommendations. In the end, all the parts are combined, but no analytical knowledge is shared across the company borders in this case. Now, let's start with the pros, right? What are the advantages of such isolated analyses? Many of those are very, very common nowadays. First of all, you don't expose any data, any information, right? Nothing leaves the company borders here. No IP is revealed. No potentially harming private data can be accessed. Second, because we have this heterogeneity in data, every unit can build its own perfect model to make sure that the data is handled in a meaningful way, right? So they all deal with that separately. That's also a big pro. On the con side, however, the outputs are based on incomplete information. If all of these vendors, all of these three entities would share the insights that they have, then they might in the end be more successful, which they currently don't do, right? Because it's an isolated analysis. Let's move to the other extreme that we mentioned, the full exchange of data, a centralized analysis. Now, what we do here is we have the same entities, but what they perform now is they pool all their data, potentially within a fourth entity, and all the data is now summarized in one large database. On that basis, a machine learning model is build, and we have a comprehensive recommendation, a comprehensive output. So that means that we can have perfect predictions because everything is available to us. We know if in entity A, in plant A, something goes wrong, we will see this immediately in our database, and the other plants can adjust to that, right? We know of delays, we know of issues with quality, and so on, because all the data is available. So obviously the largest pro here is that the outputs are now based on complete information. But what we obviously introduce at the same time is an exposure of data and information, and of course also an increased complexity. Right now we're pre-processing all these different data types in one table, so to speak, right? And also we have to transfer a lot of data now. That is especially problematic when it comes to data streams, right? Like I said earlier, high resolution of sensors. Let's say one plant is here, one plant is there. So that's definitely a big issue. These two ideas now deal as the extremes here. So no data exchange and full data exchange, or in other terms, an isolated analysis versus a centralized analysis. This one exposes data but has complete information. This one does not expose data, but it has only access to very limited information. So the question now is, how can we overcome these challenges and still be able to perform a comprehensive analysis? So what steps are there in between, right here, between these two extremes, and how can we address them? And that's something that we want to look into right now. Meta machine learning. And to understand where to position meta machine learning into the different challenges that we face when it comes to system-wide learning, let us have a look at these systemic challenges on a more quantitative view. One that you're very familiar with, a precise matrix, where we say, let's assume we have complete knowledge of a phenomena and we can aggregate the data of our system. What we then have is something that we experienced a lot as part of the lecture and the exercises. We have different instances and we have different features. And now the idea here is that different entities have knowledge of the phenomena, but this knowledge is distributed. More precisely, the data is distributed. And different things can occur here. The first one is that the features are distributed across different entities, what you can see over here right now. So they have knowledge of all the same instances, but the features are distributed. That's a case of the bank, right? Where one customer is a customer with multiple banks, has multiple bank accounts, but now we know different credit histories about that same instance, about that same customer, right? So this challenge would be, in more mathematical terms, predicting the target based on distributed features. The other challenge might be that the features are the same, but the instances are distributed across entities. So challenge B over here, training models on distributed instances. And that means you require obviously different methods for these. If your features are distributed, right, we think about building a model that has an understanding across different entities about the same instances, but with different features. Whereas in challenge B, you want to train models based on distributed instances. So the training is for the same features all the time, but we look at different instances per entity, right? Depends on how this is distributed. And of course, you have the highest challenge, which is training models based on distributed components and distributed instances. And now we want to look into a few solutions, the first one being meta machine learning. So meta learning describes a concept in machine learning where a learning algorithm, can be any one of those that we tried already, can utilize meta knowledge that is gained through experience. So we have a system that must include a learning subsystem, which then adapts with experience, right? We talk about so-called meta knowledge that is generated based on previous learning episodes. So over time, we generate more of that meta-knowledge, so we can abstract across different domains or problems over here. So in a simplified manner, we have a learning task where our system is fed with previous episodes, and what we try to do now is learn across those episodes and understand them for better solving future problems. And there are different ways in meta-learning, right? And what we're interested in are base learner combinations, so-called ensembles. That's a word you already heard if you recall the different algorithm classes when we talked about supervised machine learning cases. Now, these model combinations are often used when a bunch of algorithms would be worthwhile implementing, right? So we want to combine the strengths of existing algorithms. So we have a hard time in picking a single one. And now instead of selecting a single one, we want to combine algorithms and then somehow aggregate their outcomes. And there are three ways of doing that. The first one is called bagging, the second one is called boosting, and the third one is called stacking or stacked generalization. And let's have a look at what each of these do. Before we do that, however, I want to do a very short recap of bias and variance and the trade-off here. That's something we discussed in the evaluation lecture. If you recall, we wanted to identify whether models overfit or not. That's explicitly this discussion now again. But we want to look at it from a different perspective. We want to have the error on the y-axis here and the model complexity on the x-axis. And now what typically happens is as models get more complex, the bias increases, as you can see over there, right? So typically for very low complexity of models over here, we typically have a very high error, right? We try to fit a linear model to more complex, potentially polynomial behaviors or patterns. This model will underfit, right? The complexity of those models is very, very low. However, if we take very complex models over here, the error might decrease. Now, what we have on the other hand, though, is the other dimension of variance, which increases with model complexity. If you recall the earlier lecture, this means our algorithm tends to learn the data by heart. Instead of generalizing the way that it should, it now precisely learns every data point and does not generalize by that at all. So that means we have two errors here, the variance error and the bias error, and if we combine them, we have the total error. So that means there is an optimum here, which is the middle ground, the middle model complexity, where we have low bias and low variance, and where we actually generalize well, where we actually capture the very underlying pattern that we are interested in. And this becomes important because that was a big motivation for getting into meta machine learning in general, or ensemble models more precisely, because it was hoped that they can help with these two extremes of high bias versus high variance and finding this sweet spot where both of them are low. Now let's have a look at the first case here. And that is called bagging, which is short for bootstrap aggregating, and that was originally invented to decrease the variance of a prediction. Now, how does that work? In bagging, we have multiple subsets of the original data that are used creating a so-called bootstrap sampling. This means we randomly select samples from the original data set, the original population over here, with replacing. That means the same sample can be chosen more than once. So we create several different training data sets or sample sets. That's what you can see over here, which we take. That's the first basis. Now what we do next is we train multiple models. So each of these subsets is used to train a separate model. So for example, if you're using decision trees, each subset trains its own decision tree. And the key point here is that these models are trained independently. So we have independent models, H1, H2, Hn, and so on. And the next step now, the final step, in like it is in every meta learner, but in bagging as well, is we need some form of aggregation of the results. So once all models are trained, their predictions are now aggregated to make a final decision based on that. So for regression problems, this is typically the average of all predictions. For classification, this often means a majority vote system, right? So maybe these two over here said this part is within quality. This one said it is not. Well, then the final vote will be, if it's a majority vote system, that the part was within quality. And the idea is that by combining these bagged models, we get better than the individual model. So let's say we want to distinguish between our two classes, A and B over here, right? Fitting a linear line obviously does not work. So let's utilize decision trees and let's have three models that take their shot, right? So we have one model separating these data points because they were fed to them as a subset. We have another model, the model 2, which separates them, and we have a model 3. And now if we take the bagged model, the idea is that it does a pretty good job in separating them. Not perfect, but a good job. Now that's how bagging works. The next class over here is boosting. And the most common algorithm here is ADA boost. That is, I think, the most popular one out there. And it works with increasing and decreasing weights. So ADA boost in specific, but boosting in general, is another ensemble technique. It's similar to bagging, but it operates differently. Its primary goal is to convert a set of weak learners into a strong learner. So what we have here is a sequential model training. So unlike bagging, where models are trained independently but in parallel, now boosting involves training models sequentially, so one after the other. So each new model is trained based on the performance of the previous model, right? So we have a model that is being trained, H1, then we train the second one and the third one and so on. And what we do now between those steps is we focus on the errors. So the boosting algorithms pay particular attention to training instances that were misclassified in the case of classification, or that had a higher error in case of regression in those previous rounds. And the subsequent models, the ones that follow then, focus more on these difficult cases, on those cases where one of these models had issues with. And how it does that is by weight adjustment. So after each training round, the algorithm adjusts the weights of the training instances. So correctly predicted instances are given less weight, and instances that were misclassified are given more weight. And this makes the algorithm focus more on the difficult instances in the next round instead of the most common, the majority ones that are not that is interesting. And then the final model is a weighted combination of all those weak learners. And the weights, again, are determined based on the performance of each learner. So let's have a look at how this works, how these classifications are combined into an optimized model. So let's say you start with one weak learner, which looks like this. It tries to, again, separate pluses and minuses here, and this is what the initial classification looks like. Now, you have a look at this initial classification, and what you will do now is increase the weight of the false classifications, the ones over there, right? So we say we want to increase the weight here, that is now symbolized in bold, for the next round. Now we receive a new classification, but of course this makes different types of errors, as you can see now, right? We adjusted the weights. Now we captured all the positive classes, but not the negative ones. So what we do again is we increase the weights of the false classifications. In this case, these are those ones highlighted in bold over here. Now we will receive a new classifier, which might look like that, right? It will try to avoid these three and cut the line over here. So you see these three are not here anymore. And in the end, you combine these weak learners, and in the logic over here, we would now have a perfect classifier, which is great at dealing out that. Okay, so that's the idea of boosting. Now let's have a look at the final case, which is stacking. Stacking, or stack generalization, is another example of these ensemble machine learning techniques. It again combines multiple classification or regression models, but this time by a so-called meta-learner. So unlike bagging or boosting, which typically involve models of the same type, stacking often uses a diverse set of models. So a neural network, a decision tree, a support vector machine. And what are the steps? Well, first of all, it trains a base learners. So initially, multiple base models, you could say, are trained on the same data set. Now, these base models can be different types again, right? It can be decision tree, support vector, machine neural network, and so on. And they are trained independently. Now, what we do is we create a new data set for a so-called meta learner over there. That's this second layer of machine learning, you could call it, right? What's different now is we have a first layer of machine learning over here, different models though, and a second layer over here, which is this meta learner. So for this meta learner, we need to create a new data set. So the predictions made by each base layer is now used to create a new data set. So the output of these will be a new data set over here, which now our model HStack over here uses. So for classification, these predictions could be class labels or probabilities going into this new data set over here, while for regression tasks, it's typically numerical values. And now we train this meta learner. So this is trained with the new data set. And its role is to learn how to best combine the predictions of the base learners. So the outcome of these base learners over here, it basically learns in which cases of my data population can I trust which of my models more or less. So it learns about learning, you could say. And then this model makes a final prediction, obviously, that is based, again, on the output of the meta learner, which has learned to effectively integrate the predictions of the base models. So this one over here is what we call the meta learner, or the meta model. So what you do in a nutshell is you use model predictions from other models to create a new, hopefully more capable model. Now let us compare the three different cases of meta learners or ensemble learners, bagging, boosting, and stacking. In a nutshell, the partitioning of the data subsets works as follows. For bagging, as I said, they are randomly selected. For boosting, misclassified samples have a higher probability to be re-elected, if you recall the graphic. And for stacking, varies, right? But we do take the main population over here, typically. How do we combine the different single models? In bagging, it's a weighted average or a majority vote. In boosting, it's also a weighted average or a majority vote. In stacking, it's a second layer of machine learning. For example, logistic regression, but can be anything. We call bagging a parallel ensemble because the models are trained in parallel and then aggregated. We call boosting a sequential ensemble as the models get better over time with each single advancement, whereas in stacking you utilize both, right? You have different models at the same time, but also you have this meta model. And while the aim of bagging was to decrease the variance error and of boosting to decrease the bias error, stacking, in theory at least, hopes to help with both. Now let's come back to our initial problem, right? We want to solve the issue of data being distributed across different entities. How can we use meta machine learning, precisely stacking, to solve our problem? Now, if you recall this initial case where we have three different entities and each of these entities has their own data, now we can ask, is there an option in between isolated and centralized? And obviously there is. If we utilize the stacking, that means all of these entities build their own machine learning models. They give an output to a meta model, which is hosted somewhere else, which can then give a comprehensive output. And by that we have no exposure of data information, right? All the raw data, all the IP protected data does not leave this entity over here. The only thing that we output is a single number or a few numbers, depending on whether it's a classification or regression. That also means we decrease our processing complexity because every entity has to process its data by its own, has to create its models. The only thing that really needs to be communicated is this layer down here where we pass on the predictions and the meta model then does a general prediction across that input that it received from the other models. However, there's still one downside though, and that is that the outputs are still based on incomplete information, right? Probably it's better if a model like that would have access to the raw data up here, which it does not right now, but it only has access to the outputs. But it might be a compromise between those two extremes. And let us look at an example where we as researchers utilized meta machine learning, more precisely stacking. And this was the case of quality prediction in an industrial manufacturing line. So you had an industrial manufacturing line of Bosch Rexroth, where parts were being produced. And that was a public challenge called a Kaggle challenge. So everyone has access to that data and can play around with it. And the setting goes as follows. So each part goes through a varying sequence of 4 production lines. You can see the start over here and how it then how it flows through different lines depending on what is being produced and what the quality is. And in total, you have 52 stations. The goal now is to predict future failures in that production, and obviously do that in time and in a way that we can still intervene and reduce the number of faulty parts that are being produced. Now, reality hits, as I told you multiple times, because if you look into the data, it's not only messy, but it's also high dimensional. We see it has 968 numeric features. It has over 1,000 date features. It has over 2,000 categorical features. And again, it contains a lot of data. That's good for us. Over 1 million parts go through, which are either no scrap, right? That means everything is within order, everything is within quality, or we have scrap. That means our part is faulty. And as always, we have highly imbalanced data, right? So only roughly 7,000 parts are labeled as faulty or scrap. So that is a failure rate of below 1%. So just that you know what we are dealing with. So what we want to do now is we want to utilize a meta machine learning framework to see how well it does. So right now, we can assume that no data is shared across the lines, just as an example. And we want to analyze these distributed components, right? Each of these lines is its own entity in our logic. And what we say now is, why don't we use meta machine learning? So we have each entity with its own data. They all build their model. The model provides an output. We build a meta learner that has an output then. And we want to compare this to 2 scenarios, the ones that I mentioned in the very beginning. The isolated analysis in separate units on the one hand, and on the other hand, a comprehensive analysis, but that is the centralized case that takes all data that is available. And by doing that, we want to find out what is the potential of doing that in moving from scenario 1 to scenario 3 with this new scenario, with this interorganizational meta machine learning method. And of course, you want to show, does it work at all? So show the feasibility. But 2 things are interesting, right? So what is the improvement that we can measure to the case where we just work in an isolated setting, opposed to how much abstraction do we lose compared to a scenario where all data is available. I'll give you access to the paper where we describe it in more detail, but I'll go through it quickly now so that you get an idea. If you're interested in how that was built, again, look into the paper. It was built with different subclassifiers, which we implemented as their own microservices and with a very easy web end in the end. So what this does then is it gives you predictors for the different lines and then a cognitive predictor, the meta model on the very end, which does its prediction based on these subclassifiers. So we trained this meta learner just as I described in the stacking fundamentals. So we want to know now, how well does that perform? And let's look at the three challenges that we talked about earlier. First, data privacy. Again, the different legal entities might not be allowed or willing to exchange data across entity borders. In our case, those are the different lines. They have different shapes, as we could also see. We have categorical data, numerical data, and so on. And finally, we have the data velocity and the volume. And let's go through those challenges one by one for this case of the production line, where we utilize now a meta learner. So first, data privacy. So you can see exemplary data over here, but each subunit only has access to confidential unit data. And the only output, again, that is seen is something like that. We have an ID, an output, and a certainty, right? A very abstract submodel output that is then being aggregated in the meta unit. So the sub-entities, the lines, they only transfer abstracted information to a meta unit, to the meta entity. And of course, the meta unit processes all incoming abstracted outputs of these entities and makes a holistic meta prediction, but at no point entities exchange or expose raw data, right? So we can definitely say data confidentiality and privacy is preserved with it. So the answer is yes, only abstract predictions are performed. The other thing that we are obviously interested in is how good does it work? To do that, we utilize the Matthews correlation coefficient, which, by the way, works well with imbalanced data. And we can see that in scenario 1, with the isolated analysis, we reach an MCC between 0.19 and 0.23. And in our scenario with meta machine learning, our MCC increases, right? So MCC, the more the better, I should say that. But of course, we're not as good as scenario 3, where we have simple access to all data. So we also have this loss of abstraction over here. So what we can do say is, yeah, that looks pretty good, as only abstracted prediction outputs are being exposed outside a single line, a single entity's border. This data privacy, IP confidentiality is preserved, and only those abstract predictions can be processed, right? Data heterogeneity will not go into detail, because in stacking you still use the same data. We'll go into data heterogeneity in a second, but what we still want to look at is the data velocity and the volume. And you can pretty quickly calculate the different scenarios here of no exchange, a full exchange of data, and the meta learning. And you can see that it's way smaller over here, right? By a fraction. We only have 120 bytes compared to 4,000 bytes over here. So definitely in this scenario of the meta learning, the volume is way lower. So we can conclude that we successfully addressed two of these challenges that we face when it comes to system-wide learning with a meta learning, both the data privacy and the data velocity and the volume. And now for data heterogeneity, let's have a look at a different case. And for that, we switch the domain and look at social media profiling. Very big challenge, very typical in the social media space, is to predict characteristics of the users. So their gender, their age, their political orientation, things like that. And what we can see, why is that example suitable? Well, first of all, we want to predict a single metric like gender, age, and so on. And what we also want to do is we have very heterogeneous data. So let's say you have the profile of a person on, I don't know, Twitter, Instagram, LinkedIn, whatever, someone like here. Now, how would you make assumptions about the characteristics of that person? What would you as a human look at? One thing is definitely you might look at the posts and the way that they are written. You might have a look at the name, you will look at the photo, you will look at metadata like the post, the followers, and so on, like the biography, like other information that this person provided. But what you can see is this very heterogeneous data. and we need to find a way to process them to come up then with a final conclusion on the characteristic of that person. And for the time being, let's use gender as a predictor, because it makes it easy for us. Now, I have to make the assumption, of course, now that we only talk about gender in a binary manner, but this is solely for the example over here, as we want to deal with binary classification. That is way easier if we talk about that in a binary fashion. Now, to address that, we will now look at these different data sources over here, right? We will look at the posts that this person had. We will look at the name and the picture. And in the logic of our meta classifier, we will now build distinct classifiers. So we build a text classifier that outputs a prediction and confidence based on the post. We build a name classifier that does a prediction and confidence based on the name. And we'll make an analysis of this picture. And all of that is then combined into a meta feature vector, which gives us a meta classification. By the way, this is something that we really did for Twitter or X profiles to find out how good we are. I'll also link the paper. And what we did then is we built those two predictors ourselves, the text classifier and the name classifier. But what you can also do, and that goes back to our ideas of deployment and APIs, is to use third-party classifiers. So for the picture, in that case, we used a third-party classifier, more precisely the IBM Visual Recognition API, right? And we could integrate this then into our meta classifier. And what we can see is that we reached pretty good scores with that in identifying the gender, right? So we reached an F1 score of over 80%, pretty good recall, pretty good precision in the end. And especially if we compare this to cases where we did not have this visual identification in here, right? So you could see, you could give each of these classifiers down here. They all deal with different types of data, obviously. You could measure the impact of each of them. And in this specific case, you could see how high the impact was of adding an additional classifier that looked at the picture as well. Again, that works very much like we humans operate. We also would look at different pieces of information, different data types, and then reveal the final outcome. So this fills our last slot over here when we want to answer how well meta machine learning can address our three challenges. Now, for the case that you just saw, we could address the data heterogeneity pretty well, because for each data source type, we had one specific model that was tailored to this type of data and could also be optimized to that. And now, of course, this can be then later integrated. So this expert knowledge per data type will then be integrated into a meta model, and this type of specializing models would not be possible without meta machine learning. So we see that it could be a good idea to utilize this method to address our three challenges that we face when it comes to learning in systems. But let's look also at a different possibility, namely transfer machine learning. And first, let's go back and look at the challenges, the systemic challenges that we faced when it comes to our system that we want to look at. Again, the issue that we face here is that our data can be distributed across the features or across the instances or across both, if you recall, right? So features distributed across different entities, but same instances. Features are all the same, but instances vary, or we have two at the same time. And this obviously has different implications for the solution that we are looking at. Now, let's talk about transfer machine learning. What is transfer machine learning about? It's about the improvement of learning in a new task through transferring knowledge from a related task that has been already learned. So you can do transfer learning for object recognition, transfer learning for natural language processing, and so on and so on. To give you a precise example, let's say you already know how to skateboard it might be easier for you to learn how to snowboard then, because you can already utilize that knowledge. Or if you already know how to play one instrument, it might be way easier for you to learn an additional instrument compared to someone who has never done anything with music in the past, right? And that's precisely what transfer learning in the synthetic realm is about, to replicate this ability that we as humans also have to transfer knowledge from a related task. To get an understanding of what this means, though, let's look at different problem types for different entities. Remember, we want to solve these problems for distributed entities. Let's say entity A has the problem of image-based recognition of elements in a picture. It wants to identify faults in a part, or wants to identify, I don't know, traffic lights for autonomous driving, something along those lines. So again, this entity has its own data. It will build a machine learning model on top and will issue a prediction. Let's say there's a different type of problem now for entity 2. This has a very specific case here where it's about recognizing faulty images of parts alpha, right? In general, similar problem, but not the same. And by the way, if you recall our foundation models lecture, there would be one way to address that, right? To have a foundation model which we then fine-tune. But today we want to talk about the very fundamentals of supervised machine learning again, and how we can deal with those. So that's problem type 2.1. We have problem type 2.2 again for entity C, which is very similar, but now we're talking about faulty parts beta, right? So very, very similar, but in the end, we're looking at a slight change over here, right? And in problem type 1, it was all about elements in a picture. Now, interestingly, let's say we have problem type 2.2 again, but for a different entity. This is D, this is C, and they're interested in the same parts. What can we learn here is that these problems are different but same. And the question is, what does similarity mean here? So when can we exchange knowledge? Can we exchange knowledge here? Can we learn anything from that case to issue that one? Can we learn anything from that case over here that could be transferred to help entity C? We're definitely sure about entity D, right? I mean, they pretty much have the same problem type. The question is, do we need any adaptation for that at all? Transferring knowledge here makes definitely a lot of sense. But what about the other cases? And you can see that this similarity is important to answer if and how we can use transfer machine learning. And this comes back to the question of how can analytical knowledge be exchanged across entities. But let's start with a definition first. So what's a formal notation of transfer machine learning? We have a domain D consisting of a feature space X. You remember that from our concept drift lecture, and the probability distribution of X. And we have a learning task that's what we want to fulfill here. So predicting failures, things like that, with a set of labels and the predictive function. Now we have a domain D which consists of two components, right? Where we have D, which is consists here of the feature space and the marginal probability distribution of Px, and then we have a task that is composed of the set of all labels that we have, right? Our target and our logic, and an objective prediction function. And again, this predictive function is not observed but derived by the training data, right? We deal with machine learning over here. So with that said, what is now the definition of transfer learning? If we have a given source domain, ds, S stands for source here, and a learning task, ts, a target domain, that's the one where we want to transfer into, dt, and a learning task, tt, transfer learning helps us to improve the learning of the target predictive function of ft and dt, so our target, using the knowledge in our source domain ds and ts. And of course, there need to be differences, and there can be differences in the domain or in the task. Or in the worst case, we have issues because both differ, the domain and the task. And the insight that we have here behind transfer learning is that generalization can happen not only within tasks, but also across different tasks, right? So if we compare traditional machine learning, we would have a bunch of different tasks, And for each of these tasks, I don't know, predicting shapes over here, like circles, triangles, and rectangles, we would build our own learning system, our own model. Now with transfer learning, it says, well, we're going to look at source tasks, for example, identifying circles and triangles. And by doing that, we learn some knowledge, right, about, for example, the shape of these. Maybe there's something in learning here that is generalizable across this specific task. And then we adapt our learning system so that it can also fulfill the target. So we transfer learning concepts and try to improve a target learning task, that one over here, with knowledge that is already known from other tasks. So, for example, from other domains. And now it depends on the similarities again. And we can go into different classes of transfer learning, but we'll just do this very, very superficially for today. The first question is the task different? If the task of source and target is different, then we have a bunch of different options at hand, right? So-called inductive transfer learning, where you can have regular inductive transfer learning, self-taught learning, or multitask learning. If you're going into the realm of unsupervised learning, which we don't really cover a lot in this course, you also obviously have cases where you can utilize unsupervised transfer learning, especially if the tasks are not the same. If the domains differ, and potentially tasks are the same, you can go into the realm of transductive transfer learning, things like the domain adaptation or a sample selection in biases. But what all of these have in common, and you can dive deeper into them if you're interested in the paper, and we'll do a few of these cases in the exercise, but what all of them have in common is this general assumption that transfer learning improves the outcome. So let's say we utilize a traditional machine learning model, which has never seen anything else apart the data that we're working on. Let's say we assume that over time we reach a certain performance over here, right? That's the case without transfer. The assumption is that with transfer learning, we see a different shape of that curve, and multiple things can be observed here. First of all, a higher start. We can assume that because of the knowledge that is present already, we have a better initial performance via this already transfer knowledge. So we start higher with transfer learning. Second, we assume that the slope is higher. So the task can be learned faster if we compare it to a single point over here. So these slopes would be different. And finally, we assume that we can reach a better final performance. So the asymptote of both of them are higher. Now, let's look into the challenges of system-wide learning again, and let's see what we can already say about fulfilling our criteria. Thinking about data privacy, well, only the models are transferred, no raw data, no IP. You might ask now, okay, but does that mean that we can't infer anything about the raw data? And that is a good point, which we won't be able to really finally settle today, which we can discuss in class. But that's like an ongoing discussion. How well do models help you to look at the potentially underlying data? And can I recreate single data points from models? But first of all, in the very narrow definition that we had, no raw data is transferred, only the models. So also no raw IP, no raw potentially private data. And looking at data velocity and volume, we can definitely say that by using these pre-trained models and looking at the graph that I just showed you, we are more efficient and typically also need less data. But again, as in the example earlier, let's have a look at a precise example to judge how well transfer learning can do here. And the best way to do that is with an example that I worked on myself in the past. So we wanted to apply transfer learning in a specific domain, namely in sales forecasting. So what we did is something that you typically do in those research projects. You go out and do interviews with experts. So we have two case companies. We talk to sales experts there and say, hey, how do you predict sales as of now, what are common metrics, what are common models that you're using, how do you go about those. And of course, as a scientist, you also have to look into research, into literature, and 9 articles were of relevance there. And the specific methodology that we utilized is called design science research. So that's where you try to design artifacts that are meaningful to the space where you develop and implement them. And you look for precise requirements here, so-called design requirements. First design requirement here was we want to ensure data privacy. That was really, really important to our interview partners. The fact that data cannot leave the company, cannot leave certain branches of our company, first thing. Second, we want to reduce the data volume that's being transferred. You can see similarities here to the challenges in system-wide learning. And something that I tend to forget to mention all the time, but that's of course really important in collaboration with industry, is it also needs to lead to an increase of forecasting performance. How do we do that? Well, we addressed this with our kernel theory, with our justificatory knowledge from the field of transfer machine learning, and we wanted to instantiate this in 2 cases. One case was a sales forecasting for restaurant chains, and the other one was sales forecasting for new products. Let us start with the restaurant chains. So the task here was we wanted to predict the daily net sales for 6 different restaurants. And those restaurants belong to 2 different chains. You could say one of them was a pizza chain and the other one over here was a sushi chain. You can already see why I keep on talking about similarities and differences between domains and tasks, because obviously a sushi chain might behave differently than a pizza chain, but they are also located in different locations and so on. What do we have? We did have the daily net sales for each of these branches, and we utilized a deep convolutional neural network that worked really well with that type of data over here. The precise method that we applied is called sequential transfer learning. How does it work? So we train a deep neural network on restaurant 1, and that model is then transferred to restaurant 2 over here. Now, the first layers of the neural network are frozen, and the later layers can be refined, and then the model is continued to be trained for restaurant 2, and you repeat this step for the other ones, right? So speaking of the neural network, you can lock these layers over here and then leave the other ones open when you utilize them. And that's how we transferred the model from one restaurant to the other. So in total, we had 6 different branches. And when we do this transfer, and also here, you can look at the paper if you want to, the results show that already the base models perform pretty well. If we start with transferring models now, it can yield significant performance increases in some of those cases. On average, so transferring all the models here and there, transfer learning improves the mean average percentage error. However, there are also cases where transfer learning significantly decreases the performance. So we can see here the base model in MAPE, and now we can have a look at the worst cases of transferring model, like this one over here for branch 4, but also the best case. And you can see that for the best cases, obviously we did very well, right? If you look at the mean and the median, you can also see that on average it worked well. There is an issue, however, with branch 4. But let's first come back to our design requirements where we initially started with. So ensuring data privacy, reducing data volume, and increasing forecasting performance. Well, first of all, no raw data was exchanged and no inferences to the raw data are possible, with the small hint that this is still up for discussion, right? But for the case over here, that requirement was definitely fulfilled. Data volume, well, it was way lower to transfer the volume of a single model than transfer all the raw data. So this requirement was also fulfilled. Now, the most important one for these restaurants was obviously, did we increase the forecasting performance? And again, on average, we did, but we also identified cases where the transfer was not helpful, right? So we have to be a little bit careful with that over here. And we'll get into the difficulties there in a second. But maybe let's move first to the second case of sales forecasting. Over here, it was about predicting the prices of new products at grocery stores. We did this together with the Schwarz Group, by the way. So with the Lidl chain. So a tough task for the experts in sales forecasting there was, how do new products sell? So introducing a new product in retail is quite difficult because you don't have any data about that new product. You don't know how does it sell in different seasonal or promotional patterns. That's typically an issue. Now, that task as of now was performed by human experts, but this of course has a bunch of problems, right? You introduce human bias and problems of imperfect information, right? We as humans, we can't process as much information. You all obviously have the dependence of this single expert and his or her availability and qualification, and again, it's a lot of manual labor. So also here we applied transfer machine learning, and now we want to focus on this last design requirement, again, the performance improvement, because as this is one large chain, Lidl in this case, obviously data privacy is not as big of an issue because they can transfer the data. So what did we look at? We had 14 different bakery goods, and we had 3 years of sales, of price and promo data, and we used an LSTM because also that was what they were using already, right? So the issue is few training data, no seasonal and promotional patterns, and this will lead to very poor data quality. Now we apply transfer learning, and you can see different cases over here. So these were the first 3 weeks after utilizing the transfer models. You have the blue model over here. This is the one without transfer learning, and we tried out different configurations. If you recall the logic earlier, that was we freeze different amounts of layers. So what you can see over here is the percentage of improvement with transfer learning on the y-axis. You can see the different weeks that we worked on. The first 2 weeks were needed for adjustment, and the blue line over here is the baseline. And the different configurations over here mean we had different amounts of layers frozen in those different colors. And oh, by the way, those ones that are underlined here are weeks where we had promotional data. So what we can see first off is that there's definitely improvement possible with transfer learning, especially during the first weeks and weeks with promotion. But what we can also see over time is that some source models perform significantly worse than the remaining models. So to answer our result again, yes, we could heavily increase. In this case, it was the MSE of up to 50% in the first 2 weeks by utilizing transfer learning. But again, then later we can also see that models without transfer were not working as well. And this brings us back to the question that we saw in both of these cases now. When is transfer learning beneficial? Or more precisely, how can we know in advance if a transfer is meaningful? So in both use cases, we could show how transfer learning enables privacy preserving, volume reducing, high performing, interorganizational, so learning across entities, machine learning. However, what we can also see is that transfer machine learning does not per se improve performance in comparison to the isolated example without transfer learning. And that's interesting because this poses a computational question. So let's assume we have n entities and we have a bunch of different possible transfer paths. If you look at all the possible permutations, this leaves us with over 1,950 possible models, only in the case where we have 6 entities, right? Like we had in the earlier example. And you can see how this increases. So the logic of that is that if not any transfer is meaningful, we must be able to identify the cases of a successful, and successful is defined as performance improving transfer, prior to the transfer itself. And that's like ongoing research. How can we identify this? Is it due to the similarity of the raw data, of the metadata, for example, the location of the restaurant, and so on? So that is still something that is up for discussion. Okay, let's have a look at the final solution that is interesting here, and that is federated machine learning as a possible method for system-wide learning. So federated learning is a machine learning paradigm, just like meta machine learning and transfer machine learning. But now the model training occurs across decentralized devices or servers that all hold local data rather than any centralized data aggregation. Again, this is designed to address a few of those challenges that we discussed, like data privacy, scalability, efficiency. But it's really important that, again, that the raw data remains on devices while only model updates are shared with a so-called central aggregator that we'll have a look at in a second. So one of these examples is Gboard, the Google keyboard that you're using. So the data stays on your local device, but model updates in the way that how you utilize your keyboard, the words that you're using and so on, is sent to a central aggregator. Now, what are the characteristics of federated learning? First of all, massive distribution. So federated learning involves a large number of devices, so smartphones like in the Google keyboard case, or Internet of Things devices, sensors, each of them contributing to the model training. And this distribution introduces challenges in coordinating, obviously, updates, ensuring fairness, and managing resources across all of these potentially heterogeneous devices. Second is non-IID, so non-independent and identically distributed, a term that you might recall from your Computer Science 101 class. Now, data on each device reflects its local usage or context, leading to this non-IID data distribution. So, for example, users might use apps differently or have regional specific preferences, and this heterogeneity can hinder the convergence of global models and require strategies to balance the updates across varying data patterns, right? So people, again, taking the Google keyboard, the Gboard example, people in Britain will use different words than in the US, for example. Third, it's the third characteristic is unbalanced. So devices often contribute differing amounts of data to the training, right? So for instance, one device might collect extensive data usage while another provides very minimal input. And this imbalance challenges, of course, the effectiveness and in some cases also the fairness of model updates, and may require some kind of weighting mechanism to ensure that these contributions are comparable. Also very typical is sparsity. So many devices may participate sporadically in the learning process due to factors like their connectivity, their battery life, their user activity, in the case of smartphones again. And this sparse participation complicates the training because training typically needs consistency, and this necessitates a very adaptive aggregation strategy to make effective use of the updates. Now, two more characteristics that come from the field of big data. Uncertainty, so the device availability and performance can be pretty unpredictable, influenced by network disruptions, hardware limitations, or specific user behavior again. And this uncertainty requires very robust communication, because the users again are different when we look at their behavior. And then I think I said that already is also the limited communication, because communication between the different devices and the aggregating function servers often constrained, because a lot of these devices are distributed across the world, and it's really important that federated learning minimizes these communication overhead by only transmitting very compact updates. So these characteristics make federated learning a very promising but also challenging approach for addressing our challenges in system-wide learning, as you could see. One question remains, though, that is, how are these updates from the models combined? And to combine these updates of each of our clients that we have, we need a so-called fusion model. And this fusion model is reached by federated averaging. So how does it work in general without going too much into too detail on the notation over here? And by the way, there's a nice library from IBM which deals with federated learning. But the core concept here is federated averaging, and that's an algorithm or a method that is used to combine the different model updates from multiple devices into a global model. So you try to build a global model out of a lot of local models. So each device trains its own local model using its own data for several iterations. And what it does then, it sends the updated model parameters, not the data, but only the weights and biases in deep learning sense, to a central server. So no communication of data, but communication of the model parameters. Now this server has to deal with all of those updates and somehow aggregate them by computing a weighted average, where weights are typically based on the amount of data each device used for training, right? That can be known, not the data itself, but the amount of data. And then this aggregated global model is sent back to the devices, and this process repeats for multiple rounds until the model converges, right? So you see that's kind of a different approach. The nice thing about federated learning, however, is if we go back to our challenges, is that federated learning can address all of these challenges. There's vertical federated learning, which deals really well with distributed entities, horizontal federated learning for cases where we have the same features, but the instances are distributed across entities. And then you have a combination of transfer learning, federated transfer learning, where you can even work with cases where both the features and the instances are distributed. And if we look back at our challenges from system-wide learning, we can definitely say something about the data privacy and the data velocity and volume. Again, for data heterogeneity, you can see all models have to work on the same type of data, so that's not really a good case for utilizing federated learning. So privacy, in federated learning, we just send the local updates of the parameters are transferred to the central model. There are a bunch of security algorithms that can be utilized to increase that even further. There's this method of secure aggregation that makes really sure that also the transmission itself is secured. So we can say data privacy looks pretty good. When it comes to data velocity and volume, because of the magnitude of these edge devices like smartphones, Internet of Things sensors, the data would have a huge volume, right? It's probably impossible to transfer all these amounts of data. So in federated machine learning, this data is never transferred. Again, only the model updates are transferred, thus reducing the data velocity and volume. Okay, that was our overview. Let's have a very quick summary of what we learned today. First of all, meta machine learning. A meta learning system must always include a subsystem. In the case of stacking, that's an additional layer of machine learning, which adapts with experience. And experience is gained by exploiting so-called meta knowledge extracted in a previous learning episode on a single data set and or from different domains and problems. Transfer learning is the improvement of learning a new task through the transfer of knowledge from a related task that has already been learned. And finally, federated learning is a distributed learning technique that deals with decentralized data with a very strong focus on privacy preservation. And this brings us to the summary, right? For which of these challenges can we utilize what type of method, right? For the challenge, again, of predicting outcomes based on distributed features, so features are distributed across different entities, we can use meta machine learning or also federated meta machine learning. If we have the challenge that we always have the same features, but the entities have different instances, then we can use transfer machine learning or also federated transfer machine learning. And for the most challenging case, we can use federated transfer learning where both features and instances are distributed. And if we have a final look at the table, comparing them with regard to data privacy, data heterogeneity, data velocity, and volume, we can definitely say that for data privacy, for meta machine learning, we only exchange abstracted predictions across entities borders, preserving privacy and confidentiality. In transfer machine learning, we do transfer whole models that could have issues, but at least we don't transfer raw data. And in federated machine learning, we only transfer updates and parameters to a single model. Data heterogeneity, there's only one of our methods over here that really addresses that, and that is the case of meta machine learning that can deal with different data types, which we saw in the example of identifying user characteristics. And when it comes to data velocity and volume, we can see that all of them do reduce the data that is being transferred. In one case, we only transfer models. The second one over here with transfer machine learning. In one case, we only transfer the outputs, that is meta machine learning. And in the case of federated machine learning, we only do the updates. Okay, so that was it. I hope that gave you a good overview on system-wide learning and the different methods that we have at hand. And I'm looking forward to the next lecture. Thank you so much.